Hi, in this video we're going to be discussing sampling distributions. So what we're starting with this unit is this process called inference. And so inference is just the process of turning information into conclusions. And again, that's a very general term. That's what Sherlock Holmes does when he turns evidence and clues into solving crimes. What we're going to be doing is statistical inference, which is where we're going to use a sample and try to use that sample to describe a huge population. So just as kind of a recap, remember the population is everything. The population would be everything or everybody. And when we describe a population, that's a parameter. However, it's very unlikely that you'll be able to actually ask everybody in your population a question, so we have to rely on a sample. And the sample is our smaller, sample of everything. And our sample is going to give us a statistic, which again, that statistic relates just to that small sample. And we want to basically figure out, well, would that small sample and that statistic really represent our larger population and the parameter? Also, as kind of a quick recap, remember with our notation, for means, the population mean is going to be our mu, that Greek letter, and our sample mean is x bar. The other part we're going to be talking about a little bit later on are proportions, and our population proportion is going to be p, and our sample proportion is going to be p hat. But we'll talk about those a little bit later. I just want to make sure that, again, we kind of recap our vocabulary and our notation. Now, when we're talking about collecting our samples, the measures we're going to be concerned about are the same ones we've been concerned about for a while now. The shape, and we want all of our shapes to be approximately normal in this case. And we're going to talk about how we can make sure that happens. Because if it's approximately normal, then the center that we want to concern ourselves with is going to be the mean, and the spread we're going to concern ourselves with is going to be the standard deviation. And once we know all of that, our question is going to eventually become, well, how much do I trust that my sample actually represents that population? So the first thing I kind of want to start with in example one is just really to go through kind of the main idea or the theory behind sampling. So here I've listed a table that gives the age of the Best Actor Academy Award winner for every year from 1982 to 2017. Now we're going to pretend that this is our population, that our entire study only encompasses the ages of these actors over these 36 years. If I do my statistical analysis, I can easily use technology, and I know that the average age is 43.889 years old. So that's our population mean, is that 43.889. And I can find that the population standard deviation is 9.837. Again, I just use technology for this. The question, though, is what if I only had a sample of the ages? What if I only had some of those ages? Would my sample mean, if I only had some of the ages, still be representative of that population mean? So again, instead of calculating the average age of all of the winners, let's say I just had a small subset. So I divided these into 9-year increments. So from 82 to 90, the average age was 40.667. From 91 to 99 was 46.111. From 2000 to 2008 was 45.222. And from 2009 to 2017, we're 43.556. So clearly, we can kind of see here that none of these sample means are actually equal to my population mean. My population mean was the 43.889. Now, they're all pretty close though, right? My first one is a little bit smaller. My second one's a little bit bigger. Third one's a little bit bigger. The fourth one's pretty close, but again, none of them are exactly equal to that population mean, which means that my sample is not going to be perfectly correct, but we kind of see that it's going to be fairly close. And that is the main idea behind polling and sampling. It's that, well, we're not going to be 100% accurate. We're definitely not going to be perfect, but are we going to be close enough? And that is really the core question around this entire third unit we're going to be doing on statistical inference on chapters 8, 9, and 10. So some quick kind of definitions, I suppose. Obviously, every one of those averages was slightly different. Each x bar, each sample mean was a little bit different, which means that x bar is actually a random variable from our previous unit, which implies that x bar actually has its own probability distribution. And these are all things we kind of talked about back in chapter 6. Now, our sampling distribution, though, for a statistic is going to be one of those probability distributions. And we're going to compute that from a sample size of, well, little n. And again, that's the notation that we used earlier in the class too. And our sampling distribution of the sample mean then is going to be a probability distribution of all those possible values computed from our sample size n with our mean mu and our standard deviation sigma. So here are the important things. When I calculated all my samples, I kept my sample size at 9. We really do want to keep our sample size consistent with something like this. And I used every single data from the whole set exactly once. And then those are my 4 sample means. Again, those are the 4 sample means that we just calculated a minute ago. And let's do a little bit more statistical analysis on my sample means to help understand my sample distribution. So the mean of my sample means was 43.889, and the standard deviation was 2.074. Well, if I compare that to my population mean, well, it's the same. And that goes back to that idea that I used every number exactly once in both cases. And if I took all 4 of these numbers, which I came from the whole thing, again, my sample mean average and my population mean are going to be exactly the same. Again, that goes back to using every data point exactly once. The real change, though, is with my standard deviation. So my standard deviation of the entire set was 9.837. I had a big standard deviation when I looked at that population, which, again, is kind of to be expected. When you have a large population, you expect some variance. And if you go back and look at the table, some of those ages were all over the place. People ranged, from being in the 20s all the way up into the, I think, 70s or so, if you look back at the data. So there's a wide range of ages for the actors. But again, when I take my smaller samples, well, those samples are going to be pretty close, and so my sample standard deviation is going to get much, much smaller. And that's going to be kind of the key idea here as we start doing some of our statistical testing. So our important formulas. For the sample mean, again, that mean doesn't change. Like I said, if you took the average of all of the averages, you'd get back to what that population one is. So fairly straightforward that your sample mean is equal to your population mean. Again, it's that standard deviation here, this formula, where we need to make a little bit of an adjustment. And essentially, all we're doing is dividing by the square root of n. So the size of our sample is going to affect our standard deviation. And essentially, as our sample gets bigger, as n gets bigger, our sample standard deviation is going to get smaller. We also refer to the sample standard deviation commonly as the standard error of the mean. So to kind of see what we're talking about visually, if I have a random variable that's normally distributed, and remember, normal means that's symmetric, that bell-shaped curve, essentially what that means is that all my sample mean should also be normally distributed, which is a really, really nice feature. We know that they're still going to have that same normal shape. But what's going to happen, so again, if we look at, let's say this first graph, this is our population distribution. Obviously, we still have our mean, mu, right at the center, and we have our bell shape. And that's for the population, where it's fairly spread out. Again, we're going to expect outliers on both ends with some relative frequency here. However, If all of a sudden I'm doing my sampling and I'm doing 5 samples at a time, my standard deviation is going to get smaller, which means it's going to get much more compact. My mean, mu, is still in the center, but my distribution is much more compact. We're much more towards the center. It's going to be far less likely to have our outliers out here. And that's going to continue. If I make my sample even bigger, for example, if I ask 30 people in my sample, now we're going to assume that, and that mean is still the same, right? That hasn't changed. But the average then, if I'm asking 30 people, I'm going to be much, much closer to that mean. It's very unlikely that I end up way far outside. Again, that's kind of that idea. The more people you ask, the closer you're going to get to the average, which is going to have, again, far less variability. And so I put all the graphs together. Again, no matter what, that mean is still in the center. The mean is the mean is the mean. It's always going to be the peak. It'll always be at the center. What's going to change, though, is that standard deviation, which affects how tall that peak is and how dispersed the data is. And again, refer back to the video on chapter 7 if you want a little bit more detail on this concept. Now, the central limit theorem. This is one of the coolest theorems and probably the most important theorem in statistics, or at least statistics 1. It actually gets its own name, the central limit theorem. And so with that last example, our underlying population was normal, so all of the samples will be normal. But we know that not all data comes in, well, that symmetric bell-shaped shape. Sometimes we have skewed data. Well, what the central limit theorem states is that it doesn't matter what the population looks like. If your sample is big enough, if your sample size is large enough, and in this case, we're going to use the rule that our sample size has got to be at least 30 people or 30 points of data. As long as we have at least 30 points of data, the sampling distribution has got to become normal. So the nice part is this works no matter how skewed the data set is. So if our data set is skewed, or if we don't know what the shape of our data set is because, well, we haven't done our statistical analysis yet, as long as we're sampling at least 30 things at a time, it has to become approximately normal. And we're going to see why that's really, really important in just a minute when we actually do some statistical analysis. But I want to kind of explain with an example first about what's really going on. So the age of coins in circulation is skewed right. That means there's fewer older coins and more newer coins. So again, if you had a pocket full of change or your change jar and you were to dump it out, most of the coins in your pocket are going to be between, well, 0 to 4 years old. And you can see that over here. This first graph on the left is your population. And then obviously there are going to be some older coins, right? You'll have some coins that are 12 years old or 16 years old and maybe even as much as 24 years old. But you're not going to have a lot of those. They're usually removed from circulation by that point, but obviously some still exist. So my population here is skewed right. Now, if I were to, instead of looking at an individual coin, if I were to average the age of the coins in my pocket, that average is going to end up being normal. And so again, look at that population, right? We know that we're between 0 and 4, right? That's where most of the data lies. If I were to look at 60 at a time, well, clearly that's most of the averages are going to be between that, well, 0 and 4. And my peak is still at the same spot. But it gives me this normal shape as long as my sample is big enough. Now I chose a sample size of 60, which is, again, overkill. We only need to get our sample as big as 30. But again, that's that main idea. The average of those coins in your pocket will be normally distributed, will have that symmetric shape, even though the individual coins don't. And if you're still a little confused, because it is normal to be confused at this point, because the central limit theorem is not always, well, 100%, well, clear at first, I want to do another example. And this is actually going to be a really good example because it's going to show us what we're really doing when we're doing our statistical testing. and how the central limit theorem works. So for this example, we're going to talk about the GRE. So the GRE is basically the SAT for graduate students. If you're trying to get into graduate school for your master's degree or your doctorate, typically you're required to take the GRE, just like most students take the SATs to get into college. Now, the GRE is, well, the scores on the GRE, I should say, are normally distributed. The mean is 150. That means the average score that a student gets is 150. And the standard deviation is 8.8 points. So what is the probability that an individual student scores a 158 or higher? And would this be unusual? So again, the average is 150. Would it be unusual if a student scored a 158? So we want to always kind of go through the same checklist. Make sure our shape is normal. And it even says it in the problem that this is normally distributed, so our shape is normal. So check. Then we need to make sure that we know what our mean is. And again, the mean's given in the problem. And again, good idea to organize all this data from the beginning, and then our standard deviation. And so we're going to need all of that information. And then all we're going to do is exactly what we did in chapter 7. It's normally distributed, so we can use the normal curve. And we're just going to set up our normal curve here. So always, always, always take the few seconds to actually sketch that curve first. Remember, your mean, mu, always goes in the middle. Right? It's always the peak. And in this case, we wanted to know what's the chances of getting a score of 58 or higher. So here's my cutoff of 158 or higher. And again, it's just a matter of setting up that normal CDF. So my lower bound is 158. My upper bound is infinity, but again, I'm just going to type in a bunch of 9s. My mean is 150, given in the problem, and my standard deviation is 8.8. And then we just, well, plug it all into my normal CDF function. And I get the probability of getting a 158 or higher is 0.1817. So about an 18% chance of scoring a 158 or higher, which if something happens about 18% of the time, well, that's definitely more than our 5%, which again, we're still using that 5% as our cutoff for being unusual. So since this number is bigger than 0.05, it's not unusual. Again, we would expect students to score a 158 or higher 18% of the time. That's not an unusual thing to happen. Again, a lot of students are going to score higher. However, and again, this is the central limit theorem in action here and why the sampling matters. What if we had a testing period and 16 students took the test at the same time, and those 16 students had an average of 158, or those 16 students had a mean score of 158. Would this be unusual? So again, we know that one student scoring a 158 isn't unusual, but what if 16 students averaged a 158? Well, our shape is still normal. Again, we said it was normally distributed. That means that, again, when we do our sampling and we have a sample of 16 students, it's still going to be normal. The mean is still 150, right? That mean doesn't change just because we're doing sampling, even though notice, again, our notation is a little bit different, right? It's the mu sub x bar, because again, now we're doing a sample, so we have that x bar. What is going to change though is because I have 16 students, my standard deviation is going to change. So I take my original standard deviation of 8.8, and I now need to divide it by the square root of my sample size, or the square root of 16. So in this case, my standard deviation is going to be 2.2. Well, it's still a normal curve. I still have my lower bound is 158, my upper bound is still 99999, the mean is still 150, right? That's still right there in the middle. The difference here is going to be, if I'm looking at 16 students at a time, I expect the standard deviation to only be 2.2. I expect it to be much, much closer together. And I type that into my normal CDF, and now I get a result of 0.000138. So that's way less than 1%. That's actually going to only happen 1 out of 10,000 times. That's definitely smaller than 5%. It's definitely smaller than my 0.05. This would absolutely be unusual. We would not expect 16 students at a time to score that high, which means that, again, the College Board has these, well, these checks in place. And if this did happen, this would be unusual and they would do more investigation. And maybe the students cheated, but again, there's no proof that they actually cheated. There's just proof that this is unusual. Perhaps it was all students who studied together or something. But again, this usually gives us a good jumping off point for figuring out whether or not things are unusual. So with sampling, for the remainder of this course, we're only going to be discussing two different types of sampling. Sampling means, which is our quantitative data or numerical responses, which is that last example we just did, right? The scores on the GRE are numerical, right? But the other one we're going to be looking at are sample proportions, which is our qualitative data. And typically think whether or not the answer that someone would record would be a yes or a no. Right? When you're doing your survey or you're doing your study, are you recording numbers or are you recording people saying yes and no? Now, it's going to be really important to distinguish between the two of those because, well, those differences are going to kind of keep popping up. And we're going to look at those differences in Chapter 8. We're going to look at those differences in Chapter 9 and those differences again in Chapter 10. And you're going to see there's a lot of overlap because regardless of the sampling type, we always need our samples to be independent and approximately normal. It's just that there might be slightly different ways that we go about that. So the first one, to ensure that our sample is independent, we need to require that our sample size, which is little n, is no more than 5% of the population size, big N. And there's the numerical or mathematical way that we state it. Little n is less than or equal to 0.05 big N. And again, with most sampling, this is kind of obvious. Most of the times you don't really have to go through this step because, for example, there's roughly 210 million adult Americans. And so what's 5% of 210 million? Well, 10.5 million. And are you going to get results or are you going to get 10.5 million adults to actually answer your question? Well, not really likely. So obviously your sample is going to be independent. Similar for things like college students. There's 76 million college students in America. So are we going to, is your sample going to ask enough people that it's more than 5%? Well, probably not. The reason this independence, though, is important, the reason we do want to make sure that our sample size is big enough but not too big. So, for example, in this class, 14 out of the 25 students are male. So that means the probability that a student in this class is male is 14 out of 25, which is 0.56. However, the probability that the next student is going to be a male, well, again, if we go back to our probability chapter, we already counted that first male, so now there's only 13 left. And out of the 24 students in class, and if I do that, now the probability that the next student is male is 0.54. These are two different probabilities. The probability changed just because I counted someone. That's a problem if you're trying to do statistical analysis. This would not be an independent statistical analysis because by observing and by counting someone, I actually changed the probability for the next person. Yeah, and like I said, this is typically not going to be an issue at all, but it is something that you want to be conscious of, and MyStatLab is going to ask you to verify this in a few cases. Now, for the approximately normal shape. Now, we talked about that first one. For sample means, our sample is going to be approximately normal as long as our sample size is at least 30 by the central limit theorem. And for the sample proportions, well, we actually talked about this already back in chapter 6. We know that with a binomial, and think yes, no questions. Think proportions, right? Success, failure, yes, no. We know that it's going to be approximately normal as long as that inequality n times p times 1 minus p is going to be greater than or equal to 10. Now, if we do know that the population is normally distributed to begin with, we don't really have to do that. But again, these are the ways that we check. So, sampling proportions. When I actually do a sample proportion, when we ask a question, we have a sample size of n, and each individual is going to either answer yes or no, a success or a failure. Again, this is a binomial type probability, and so our sample proportion, which is given as this, which we say as p hat, because see p with the little hat on there. That's our sample proportion. Remember, P is our population proportion, P hat is our sample. And the whole idea is that, again, we're going to try to use P hat to estimate our population proportion, P. So our formulas. Well, the average of all the P hats has got to be the actual parameter. So our mean in this case is still whatever that population proportion is, which is P. So again, it's the same as kind of the sample means. It's not going to change. What does change is our sample standard deviation. And it's going to change in kind of the same way. The standard deviation is going to get smaller as our sample size gets bigger. And so this is the formula that we're going to use with all of our sampling in chapters 8, 9, and 10. So let's take a look. So according to a new poll, 39% of college students think that marriage is obsolete. I want to poll 100 Tunxia students about whether they think marriage is obsolete. So the first thing I should probably do before I even answer any questions is try to make sure I've taken all the data possible out of this problem, which would mean in this case, well, my sample size and my population proportion. So my sample size is 100, 39% of college students. Well, again, I got to convert that to a decimal, so 0.39. So my proportion is 0.39. And now I can start answering some questions. So question 1, would our analysis be independent and would our analysis be approximately normal? Independent is easy because clearly 100 students is less than 5% of all students. It's less than 5% of all students at Tunxis or 5% of students in Connecticut or 5% of students in the country. Clearly 100 students is less than 5% of all students. So the next one is to figure out whether or not it's going to be normal. Now, the important question here is, of course, what are we asking? Well, we're asking students, do you think marriage is obsolete? Your result is yes or no. That's that binomial idea, right? There's only two possible cases. Either you say yes or you say no. So this is a qualitative type problem, and clearly we're dealing with proportions here. So to assure that it's normal, we're going to use that n times p times 1 minus p and make sure that's greater than or equal to 10. And, well, we're just going to use the numbers that are in the problem. We're going to substitute 100 for the n and 0.39 for the p, and then it's just a matter of order of operations. Check it on your calculator, and yeah, sure enough, 23.79. Is that bigger than or equal to 10? Of course it is. So we get a big check mark for normal. We get a big check mark for independent. We can actually continue on with our analysis. What I would recommend, if you're following along with this video, make sure you're actually following along with your calculator too. A lot of the issues in this section come from just typing things in your calculator a little bit off. Your calculator follows the order of operations as it's programmed to. That doesn't mean it's necessarily going to do it the way you do it. So just be really careful and practice as you're actually watching this video so that you can make sure you're actually typing things in the correct way. Otherwise, you'll get questions wrong on my math lab and not know why. You can understand all the processes, but if you type something to your calculator wrong, you're going to get the wrong answer no matter what. And again, your calculator is awesome. Your calculator is so useful, but your calculator is not going to do what you want it to do. Your calculator is going to do exactly what you tell it to do based on, well, how the calculator works. But now that we know that it's independent and it's approximately normal, I can start asking some questions. So what is the probability that fewer than 38% of Tunxia students believe marriage is obsolete? So, well, the first thing I have to do is calculate a few things. So first of all, my mean, right? The mean of p hat would be my p, or my population proportion. So that's 0.39. Then I have to calculate my standard deviation. And again, it's just a matter of plugging in p is 0.39, n is 100, put it in the right spots, follow the order of operations, and make sure that you get the correct answer. So you should get 0.04877. Like I said, you need to be typing that into your calculator as you go. Pause the video, type it into your calculator. Did you get the same thing as me? Good. That's a very good sign. We can move on. If you didn't, go back, Follow the order of operations. Do it one step at a time if you need to. But make sure that you get this answer before you move on to the next part of this problem. Well, we know it's approximately normal, so we're going to use the normal curve. And in fact, the normal curve and what we did in Chapter 7 is going to be the majority of what we actually do in Chapters 8, 9, and 10. It's just going to be figuring out how do we set that normal curve up. So we wanted to say, what about at 38% of college students or fewer at Tunxis? So again, fewer, we're shading the left-hand side here up to 0.38. So my lower bound is negative, a big number. And I just typed a bunch of 9s. My upper bound is 0.38. My mean is 0.39. My standard deviation is the one that I just calculated a second ago. We type that all into our normal CDF, hit enter, and we should get 0.4188. All right. Now, would it be unusual if more than 42 Tunxis students believe marriage is obsolete? Well, I got to calculate here. And I have to calculate what p hat is. I have to figure out what my sample proportion is, which is just that x over n, the successes over the sample size. So 42 students said yes out of the 100 students we asked, so p hat is 0.42. This is commonly referred to as our test statistic, right? Because I'm trying to test whether or not my statistic is unusual or not. All right, so we're doing a test statistic. And again, p hat is absolutely going to be a statistic, right? Because it's just a sample. It's that 100 students that I asked. But once we have that, it's just setting up the normal curve. It all goes back to that normal curve. So now we said 42 students or more, and would that be unusual? So again, we're shading to the right here of that 0.42. So my lower bound is 0.42. My upper bound is a very large number. My mean is still the same. My standard deviation is still the same. We type that in, and I get 0.2692. Now remember, we want to know whether or not that's unusual or not. And so, well, if I move the decimal place over 2 spots, that happens 26.92% of the time, which that's definitely bigger than my 5% threshold, or my decimal is bigger than 0.05. So this is not unusual. All right, and that's basically all we're doing in Chapter 8 is trying to set up problems like this. So take your time. My suggestion is always, always, always sketch that normal curve. Give yourself a sketch so that you understand what's going on first. And then a lot of it's using the calculator. So you're going to have to practice pressing those buttons. That's a skill in this section, is making sure you're pressing the right buttons in the right place. So again, just take your time. Work slowly, and if you have any questions, please let me know. Good luck.